Hey guys, welcome back. We are on day 18. We're going to talk about a couple things here. First, we're going to revisit molar mass. Then we'll talk about mass percent. And we're going to do empirical and molecular formula problems. All right, so day 18 and 19 are basically one long day, right? One long lesson, lots of examples. And so let's dive in. So let's revisit molar mass, right? The mass of 1 mole. And why do we do molar mass? Well, we have to weigh to count, right? We can't count individual water molecules or individual atoms or individual formula units, whatever we're talking about. We can't count these molecules and compounds. So we have to do the molar mass, right? And so the molecular mass, right? So H, if you use your periodic table, again, you'll need your periodic table for day 18 and day 19, right? The molecular mass is 1.008, right? I will use 1.01. So 2 times that plus 16 would be 18. And I would just round it to O2, right? O2 AMU. But it's also 18.02 grams per mole. And we're going to do that, right? And remember, mass divided by molar mass is moles, right? And so we'll do mass percent. We're going to do mass percent. And right, again, because we count by weighing, right? And we do count by weighing. Count by mass. All right, so mass percent. Elements percentage of the compound's total mass. So the mass percent of A, right, would be the mass of A in 1 mole of compound all over the mass of 1 mole of compound multiplied by 100%. That's it. All right? So, for example, if you ever had 925 silver, that's 92.5% Ag, which is there's 92.5 grams of Ag and 100 grams of sterling silver. So there you go. That's that mass percent. That's what we'll use it as. It's a ratio, right? It is a ratio. Just like molar mass is a ratio. We like ratios. All right, so calculate the mass percent of sodium in sodium oxide. The first, very number one important step, because we do this in class all the time, and people just dive in to solve problems, right? Because a lot of times you get to chemistry, you're pretty good at math, you're pretty good at solving problems. You see sodium, you see oxide, you know it's oxygen, so you put Na down and you put O down and you start doing the mass percent. The first thing we have to do is make sure we have the correct molecular or chemical formula. Correct, in this case, chemical. It's an ionic compound, so correct formula of the compound. Sodium, Na plus. Oxide, O2 minus. So this becomes Na2O. That's very important, right? Because you'll get a drastically different mass percent of sodium if you do NaO or NaO2. All right, so the percentage of sodium. All right, and so there are 2 sodiums, so 2 times the molar mass of sodium. And the molar mass of sodium would be 22.99 grams per mole. So 22.99 grams per mole down here. Now you can do this. Where you actually don't put the whole molar mass down there. Or you could do the math. 2 times 22.99 plus the 16. All right. Either way, you do it. Take a second, pause, do it in your calculator real quick, see what you get. Hopefully you got 74.19%. Hopefully that's what you got. If you didn't, try it again. All right, and then we'll move on. All right, next, compounds. All right, stoichiometry of compounds. The composition of a compound is indicated by a formula. All right, it's the relative number of atoms of each constituent element. All right, it's the mole ratio. Mole ratio. All right, it's a particle ratio. So we have sodium acetate. So what sodium acetate is, right? Sodium Na plus, acetate C2H3O2 minus. So that's sodium acetate, right? We got one sodium atom, 2 carbon atoms, 3 hydrogen atoms, and 2 oxygen atoms in a molecule, or 1 mole of sodium, 2 moles of carbon, 3 moles of hydrogen, and 2 moles of oxygen in a mole, right? And so recall mass divided by molar mass is your moles, your ratio, right? Because you have grams for mass divided by grams per mole, right? And that would equal the mole, right? And so calculations, typically, right? Calculations usually, typically involve, right, converting a mass ratio into a mole ratio. We haven't talked about chemical reactions yet, but that's what we're doing. We're measuring mass, but they react in moles. And so we have to get to moles. Now, the formulas. And we covered this, but we're going to dive in again. The molecular formula, right, is the actual formula of a molecule. In this case, benzene C6H6. All right? Okay. The structural formula, coming up soon, but not yet, is how they're put together. That shows how they're bonds. And the empirical formula is the simplest ratio, right? It's the simplest ratio, right? And all ionic compounds are expressed as empirical formulas. All right, so let's do an example. Actually, a bunch of examples from now on. Right, calculator definitely needed. An oxide of copper. Well, what do we have there? We know we have copper and oxygen, right? And so we have oxygen and we have copper. And it's that much copper by mass. What's the formula of the oxide? So now, this mass, right? This mass percent. It is 88.82 grams of copper per 100 grams of sample. Or our copper and oxygen, which is Cu and O. We just don't know how many Cus and how many Os. And the reason we don't know that is because copper can take more than one charge. In fact, copper can be +1 a lot of times and +2. Both of those exist, real life examples. Well, if that's the case, right? How do I know which one? Well, we're going to find out with the mass ratio, right? The mass ratio gives us that, okay? And so now, right, because we have 100%. So if I have 100 grams, if I assume 100 grams, just assume 100 grams, which is the best thing to do, that gives me, I have 88, no, wrong color here, orange for copper, 88.82 grams of copper, which leaves me with how many grams of oxygen, right? Well, what is 100 minus 88.82, right? So we'll do the 100 grams total minus the 88.82. And that looks like it's 11.18 grams of oxygen, right? Because they have to total 100%. Right? And since I have 100%, we're just going to assume I can have the 2 decimals, right? That's not a sig fig situation. So now if we do this, I have grams. I have a gram ratio. I have my mass ratio. So to have mass ratio, need mole ratio. So you divide by molar mass. So the molar mass of copper, I look, it's 63.55 grams per mole. And for oxygen, 16. All right. And so if we do this, I get 1.398 moles of copper. And it looks like I get 0.6988 moles of oxygen. And so now I have a mole ratio. That's fantastic. The problem is it's not whole numbers. So step 3, I need to make mole ratio whole numbers. So you divide by the smallest. Get the whole number ratio. Well, the smallest here is 0.6988. If I do that, it looks like I get 2 for copper and 1 for oxygen. So that means my empirical formula will be Cu2O, which is copper with a charge of 1 oxide, right? Copper 1 oxide. Now, I need to pause here because I always tell students this. I got 2 and 1. What if I had got 1 and 1.5? What if I'd have got, instead, and I'm going to erase this, but 1.5 here. Can I just round that up to 2? The answer is no. You'd have to double both. If I'd have got 1.33, I can't just round that down to 1. I have to triple both. All right, I'd have to triple copper and oxygen. All right, so when we get fractions, if you get 0.25, right? Now, if you get 2.01, 1.98, that's 2, right? That's 2. You're rounding that, okay? But you get like 0.2, all right? You get more than even 0.1, right? Check. Sometimes you're not using enough decimals, right? We're not using enough sig figs. And sometimes we need to round differently. All right, so I just wanted to point that out. Let's do another one. A compound of boron and hydrogen. All right, so I have boron and hydrogen. We have boron, and we have hydrogen. And it's that much boron. What is the empirical formula? And the molar mass is 27.7 grams per mole. What's the molecular formula? All right. Well, this looks like an extra step. Because we have a molecular compound, right, the empirical formula may not be the molecular formula, right? In the previous one with copper, the empirical formula is the formula because it's ionic. Here it's not. All right, so I have boron and hydrogen. And we know we have 78.14 grams of boron, right? Because, again, it's 78.14 grams of B per 100 grams of sample. Well, that's how much boron. How many grams of H do we have? Well, they should add up to 100. So what's 100 minus 78.14? I got 21.86. So now I have grams of boron and grams of hydrogen. What did we do last time? Well, last time we have a mole ratio or a gram ratio now. We need to get the mole ratio. And I divide by the molar mass. Right? So I'm going to divide by the molar mass of each of these. Now for boron, I got 10.81. I have 4 numbers here. So for hydrogen, I will use 1.008 grams per mole. So now I can keep my 4 sig figs. I believe in this case it doesn't matter, but it's always a good idea to keep the number of sig figs. And so 78.14 divided by 10.81, I got 7.228. And 21.86 divided by 1.008, 21.64. Grams, moles. Now we divide by the smallest, right? To get the whole number ratio, because I have a mole ratio now, but it would be it'd be weird if you saw B 7.228, H 21.64. That would be weird. We don't see that. Okay, we see whole numbers. So we divide by 7.228, and for B we get 1. And for H, it looks like we get 3. So the empirical formula is BH3. I want to know what the molecular formula is. I just know it's 27.7 grams per mole. I know that the empirical formula is a multiple, is the lowest ratio of the molecular. So the molecular is, right, a multiple of the empirical. What is the molar mass of BH3? All right, well, I have 3 hydrogens and 1 boron. So that's 10.81 plus 3 times 1.01. Right, so I got 13.84, I believe. Yeah. So my question then would be, how many times does 13.84 go into 27.7? So I would take my 27.7 divided by my 13.84, and it looks like I get 2. So, right, because since that's a times 2, this is a times 2. So it looks like my molecular formula would be B2H6. And that's it. And so we're just figuring out how many empiricals make up my molecular. How many empiricals make up the molecular? And in this case, it's 2. All right. Moving on to number 3. What is the percent by mass of nitrogen in ammonium nitrate? Step 1. What is ammonium nitrate? Ammonium nitrate. So ammonium, NH4 plus nitrate, NO3 minus. Well, if that's the case, they're good. So it's NH4, NO3. And I'm looking for, I got 2 nitrogens in there. All right. So percent N. I have 2 nitrogens. plus I have 4 hydrogens, and we have 3 oxygens. So my nitrogens will be 14.01. I have hydrogen, which is 1.01, and oxygen, which is 16. Now, like, if you need to, go percent N equals 2N all over 2N plus 4H plus 3O times 100%. Do that. Right? Go ahead and do that. There's nothing wrong with doing that extra step. And if I do this, I get 35.0% N by mass. All right. Depending on your calculator and your calculator techniques and skills, you might have to do the bottom first. You might be able to do it all at once. All right. That depends on how comfortable you are with the calculator. So that's number 3. Number 4. What is the average mass? Here's a question. What's the average mass of a single molecule of ethanol? And then, do all molecules of ethanol have the same mass? All right. Well, ethanol. All right. I have carbon, 12.01, plus 3 times 1.01, plus another 12.01, plus 2 times 1.01, plus 16.00 for oxygen, plus 1.01 for hydrogen. And so if we do all that, it looks like it's 46.08 grams per mole. So I'm going to rewrite this as 46.08 grams of CH3CH2OH per 1 mole of CH3CH2OH. Now, what are we looking for? We're looking for the mass of a single molecule. I have the mass of a mole of molecules. So the top, this is fantastic. That's not fantastic. I have to somehow get rid of mole. Can I do that? Well, 1 mole of CH3CH2OH happens to be 6.022 times 10 to the 23rd molecules. And so now we're in mole or grams per molecule. If we do that, I get 7.652 times 10 to the negative 23rd grams per molecule of CH3CH2OH. So that's what I get with the grams per molecule. Now the second part of this question, do all molecules of ethanol have the same mass? Well, what did we just calculate? The average mass. Well, if there's an average of something, we would assume not everything's the same, all right? And the answer, one-word answer to this question is isotopes. So it's no, right? We have isotopes, so they have different numbers of neutrons. So you could have some ethanol with a couple more neutrons, and since this number is so small, 7.65 times 10 to the negative 23rd, right, having an extra neutron or two makes a difference, okay? So the answer is no to that one. All right, number 5. We're going to do number 5, even though it says day 19, and then we'll go on to the next one. All right. Sulfur reacts with fluorine to produce something called SFX. What is X? Well, this is a good one, right? Because there's more than one real sulfur fluoride compounds. All right, how do you do this? Well, we haven't balanced equations yet, and we can't balance this equation because we don't know what x is. I'm sure you can write some fancy math equation, but it's not worth it. What does excess mean? So we have excess here, right? We have excess. That means I have plenty of fluorine. I have extra fluorine. What do we know? We know that much sulfur. Now, there is something called the law of conservation of mass. So that means if I have that much sulfur here, how much sulfur do I have on the other side? See, in red, this is grams of sulfur and fluorine. I can take this over. We can subtract out the 1.256 grams of sulfur. And that is going to give me, if I do the math, 4.466. Right? Because law of conservation of mass, that's what we have. So now we know we have 1.256 grams of S and 4.466 grams of fluorine. Well, this should look familiar. We have a mass ratio. I don't have to assume 100 grams. I don't, right? This is the actual sample, and we know the actual sample. So I still have to go to moles. All right? We still have to go to moles. So sulfur is 3207. And fluorine is 19. All right? And if we do this math, I get 0.0392 moles of sulfur. And we get 0.2351 moles of fluorine. Fantastic. Now, just like we did before, we're going to divide by the smallest to get a whole number ratio, 0.0392. And we get 1 for sulfur, and it looks like we get 6 for fluorine. So X is 6, so it's SF6. All right, so there's 1 through 5. We're going to stop there, and we'll do the rest of the problems in the next one. If you have any questions, feel free to reach out. Otherwise, we'll see you next time, guys. Take care.